So if everybody's ready, we'll get started now. This is where we ended last time. We were talking about the symbols that we use, and E parentheses X is read the expectation of X. It's the same thing as mu, and because you see that Greek letter mu, you know this is a population. Probability distributions are referring to the population. It refers to the whole entire group, not just a sample of something. And the variance of a discrete probability distribution is either VAR parentheses X or just sigma squared is fine also. And the standard deviation of a discrete probability distribution is sigma. We're going to get mu and sigma both using the calculator. You're not going to need a formula for that. If you do need to find the variance for whatever reason, then you find the standard deviation, being sure to use the one with the population. And as you're going to see, hopefully that won't be a problem. You're going to take your population standard deviation and square it. So we're going to use the calculator to do everything. We're going to start with this first example. Survey asks a sample of families how many TVs are in their household. Now, I have no idea what teapots have to do with TVs, but it was there. And it says to determine if this sample is a discrete probability distribution. Well, in order to determine that, the first thing we look at, remember there are two rules. All your probabilities need to be between 0 and 1. None of them can be negative, none of them can be worth more than 1. So are all these probabilities, and they're the ones that are here, which are listed in the table, both, are all the probabilities between 0 and 1? Yes. Yes. Okay, then the second rule is that the sum of all the probabilities has to add up to 1. So do these add up to 1? Okay, so since they do add up to 1, it satisfies both of the requirements, and the answer is yes. So the next thing that it says is the expected value, E of X, which is also the mean, is equal to the predicted number of televisions for an average household, and we need to find out what that is. This is how we're going to do that. We're going to go to the Stat button and press Enter to edit. We're going to go over to List 1, and we're going to enter the values of X, which is 0, 1, 2, 3, 4. Then we're going to go over to List 2, and we're going to enter the values of P of X, the probability that X takes on that value. Okay? And if you have your calculator entered and all your data is entered, and you make sure that all the numbers are right, then the next thing that you do is you hit your Stat button again. You right arrow over to the Calculate menu. This is where some formulas are. We're choosing one variable, statistics, because the variable is how many televisions are in a family's household. And the X values are in List 1. And the y values, or the p of x values, the probabilities this time, are in list 2. And then when you hit enter, it tells you that the expected value is 2.17. That tells you that the expected value, or the mean number of televisions per household for the population that these families came from, is 2.17 televisions. You do not round that off to 2 televisions. That is 2.17.
What button did you hit though whenever you done after you put your numbers in?
You hit stat and then go over to the middle menu, calculate, and press enter. Then list 1, then a comma, then list 2, and then enter.
Sorry about the emergency.
It's okay. Sometimes things happen. Might need this. Now notice that even though the calculator symbol is X bar, you have to know that because it's a probability distribution, that it's going to be mu or e of x. Calculator symbol isn't necessarily going to be the right symbol. It's the same formula, and the calculator doesn't use multiple symbols for the same formula. And then it says, what is the standard deviation? Notice you don't even have a sample standard deviation. The reason for that is because when we put decimals into the list 2 column, the frequency column, the calculator assumes that that's a probability distribution. And therefore it assumes that that is a population, and it doesn't even calculate your sample standard deviation. It leaves that blank. So the standard deviation is sigma. It is not sigma x bar, it is sigma. And it's 1.158 05872. Which it's okay to round off, in this case, to 1.158. And if my stat lab tells you to round off differently, follow whatever directions it gives you. And then the last question is about the variance. And the variance is the value of the standard deviation squared. So you want to type in all those decimals, not the rounded off answer. And then you want to square it. And that turns out to be 1.341. And it's again okay to round that off to 1.341. And in my stat note, just be sure that you follow the rounding directions. Okay? Now, if you need a reminder of how to do this, it works just like the directions on page 7, the 2 previous pages from where I told you to start. It's just that was for a frequency distribution, and this is actually a relative frequency distribution, but it works the same way. You can also use that same thing to get a weighted mean. You don't have to do the formula to get a weighted mean. You can actually put your values in list 1 and the weights in list 2, and you can get the weighted mean that same way. Here's our next example. I think this is where the peapods are supposed to be. So the following table lists the numbers of peas with green pods among 8 offspring peas. So what they've done is they've planted some peas, and not all of them apparently yield green pods. Some of them maybe yielded a different colored pod, white or yellow pods. So it says determine if this is a discrete probability distribution. How do you know if it's a discrete probability distribution? What do we need to check? We need to check those two requirements. Now the first one's easy to check because you don't see anything that's 1 point something, so it's nothing more than 1, and none of them are negative. And the 2 0 pluses that you see here says it's essentially 0. What's happened is if you round it off to 3 decimal places, it rounds off to 0. So the first requirement is definitely met. The second one we can check actually using the calculator. And we don't even have to add them up. We'll just go over and edit the data. So it looks like we've got 0, 1, 2, 3, 4, 5, 6, 7, 8 for our possible number of green pea pods. And then the probabilities are 0, 0, 0.004, 0.023, 0.087, 0.208, 0.311, 0.267, 0.100. Now the one thing you need to be sure is that these are the same length, because remember the table over here, you have just as many x values as you do probability values. Those have to match. They're paired up. So then we'll hit the stat button, and we'll go over to calc, and we'll calculate one variable statistics for list 1, comma, list 2. Remember, you have to have both lists because it's probability distribution. And the way that we know that adds up to 1 is because it says that n is equal to 1 right there where I left my cursor. What that does is it adds up that column and says that that column actually is equal to 1. Okay? So yes, that is also satisfied, and the answer is yes. So now we have the expected value, E of x, which is the mean, which is 6. And the standard deviation is 1.222. And if we round it off to 3 decimal places, which is plenty of decimal places, then it's just going to say 1.222. And then the variance is going to be 1.222292927. And then I'm going to square that. So the variance is sigma squared, and that's 1.494. Because 1.4939 rounds to 1.494. Okay? Yes, ma'am.
What's the difference between x and e of x? Like the
X is the actual values. It's the possible number of pea pods. If you're talking about a total of 8 pods, it is possible that none of them are green. It's possible that 1 of them is green, 2 of them is green, 3 of them green, and so forth. E of x is if you were just guessing, looking at that table, and it's actually good that you asked that question. If you were just guessing, looking only at this table, at how many of those 8 pods you thought would probably turn out to be green, what do you think your best guess would be? Which one has, well, it would, that is the absolute best guess. But looking at the probabilities, is it likely that you're going to have 0, 1, 2, or 3 that are green? Is it likely that all 8 of them are going to be green? Which one has the highest probability? 6. Followed very closely by 5 and 7. So if you were guessing, looking at that table, how many were likely in the next group of 8 to be green, you'd say, well, probably 6. And that turns out to be the value of the expected value, or the mean. Okay? So that's why this is called E of X, or the expectation. This is the expected value of the X's, and X represents the number of peas with green pods. Okay? The question below that says, use the range rule of thumb to identify a range of values containing the usual number of peas with green pods. The range rule of thumb says you take the mean minus 2 standard deviations to the mean plus 2 standard deviations, and 95% of the time your usual values are going to be within that range. And since my mean is 6 and my standard deviation is 1.222, then I'll do a little arithmetic. And the usual number of green pea pods that I would, 95% of the time, if I were to grow these pods over and over and gather handfuls of 8 of them, then 95% of the time there should be between 3.556 or 3.6 would be probably close enough to about 8.4. And what that tells you then is that if you were to have a randomly chosen handful of 8 of these pea pods, and you were to only have 2 pea pods that were green, then that would be a very unusual occurrence. That would occur less than 5% of the time. So that's not a usual thing. That's not an expected value. The expected value would be somewhere between 3.5 and 8.4, which says, you know, somewhere in here. And notice the probabilities for anything less than 3 are all very, very low. Okay? So it says, based on that result, is it unusual to get only 1 pea with a green pod? Yes. Because it is expected to occur less than 5% of the time. Or the probability for getting less than 3 is under 5%. Something that references that very low probability. Okay? Is this making sense to everybody? Okay, we're still working on the same problem. So it says find the probability of getting exactly 7. Well, you can read that out of the table. The probability of getting exactly 7 peas with green pods is 0.267. But if it switches and asks us find the probability of getting 7 or more, that's the probability that x is equal to or greater than 7, which would be the probability that x is equal to 7 plus the probability that x is equal to 8. And there again, out of the table, we can read the two probabilities. And the probability that x is equal to or greater than 7 is 0.367. You just add those two probabilities together. Because the only two outcomes that are equal to or greater than 7 are 7 or 8. And that's why you add the probabilities. And then our last question for that page says find the probability of getting less than 4. Okay, the probability of x being less than 4 is the probability that x equals 0, 1, 2, or 3. So we would add all those probabilities together. So that would be 0 plus 0 plus 0.004 plus 0.023, which says the probability that x is less than 4 is equal to 0.027.
Can you push the paper?
Yes. Better close my parentheses. Okay? And keep in mind here that the probability that x is less than 4 is exactly the same as probability x being equal to or less than 3. That means the same thing. Okay? That's why we spent all that time last time doing the writing the inequalities and figuring out what they meant. Any questions?
Is there a method that you prefer us to use, like less than or equal to 3, or?
No, it means the same thing. I just wanted you to be aware of this because when we come to the binomial problems and start using the calculator, there's two functions, and knowing that these mean the same thing will help you choose between the two functions. Now we're going to talk about something called a binomial probability distribution. So the first definition, a binomial experiment is a probability experiment that satisfies all these conditions. There's a fixed number of trials that we're going to call N. in the last problem that we were looking at, that might have been a binomial probability distribution, because either the P's were green or they weren't, and the fixed number of trials would have been the 8 P pods we selected at random. The trials are independent, which means that the outcome of one choice doesn't affect the outcome of the next one. And this is very important. Each trial only has 2 outcomes. The outcomes are classified as a success, which is denoted by S, or as a failure, which is denoted by F. Don't associate success with being something good and failure being something bad, because that might not be what it is. Success means that if you're counting green pea pods, success is that the pod's green. Failure is that the pod's not green. Okay? If you are talking about the number of patients that are that have surgery performed on them in a certain kind of surgical procedure, success might be that the patient lived, failure might be that they died, or success might mean that the operation worked, and failure means that it didn't. But it's not always something that's good or bad. The probability of success is called P of S, because it's a probability, and it's called lowercase p. The probability of a failure is given the symbol lowercase q, and p plus Q is going to equal 1, because either you succeed or you fail. Nothing else can happen. Either the P pod was green or it wasn't. Okay? The variable here, X, counts the number of successful trials. So that means, for example, with our 8 P pods, we could have had no successes, 1 success, 2 successes, 3 successes, 4 successes, 5 successes, 6 successes, 7 successes, or 8 successes. So it always starts at 0, and it always ends with the total number of trials. And the central problem that we're going to look at in these problems is to find the probability of X successes out of N trials. Now, if you've got a binomial experiment, you don't have to plug all the numbers into the calculator to get the mean. But this only works if it is a binomial. If you need the mean of a binomial experiment and you have no reason to plug all the other numbers into the calculator, you can find the mean of a binomial experiment, which is still an expected value on U, and it's going to be N times P. The number of trials times the probability of success. So, for example, if I were talking about the probability of passing the next test, either you pass it or you fail it, and if I had 10 students and the probability of passing the test is 70%, then how many of those 10 students do you think would pass the test if the probability of passing is 70%? Does it make sense that it would be 7 students? And that's really what that's saying. Now the variance is actually sigma squared, and you can calculate it by taking N times P times Q. Q, the probability of failure. Now there's no reason, there's no logic behind that one. It isn't like the expectation where you can kind of make sense of it. That's just a formula. I will not make you memorize that formula. You will have formulas on the next test. But that also means then that the standard deviation is going to be sigma, and that means it will be the square root of n times p times q. Because remember, the relationship between variance and standard deviation is the variance is the standard deviation squared, so the standard deviation is the square root of the variance. Okay? Now we're going to do all of these kind of problems on the calculator. Totally on the calculator. So here's our first example. We have an experiment where a soccer player who historically makes 60% of his penalty kicks is asked to kick 3 penalty kicks, and the number of penalty kicks that he actually makes is going to be recorded. Find the probability that the soccer player makes 2 of his penalty kicks. Is this a binomial? Okay. How many possible outcomes are there when he kicks the ball?
2.
Which are?
He can either make it or not make it.
He either makes it or he doesn't make it. So that's success and failure. Okay? Does the probability of him getting his next kick have anything to do with the probability he got his last one?
Yeah.
No. So those are independent trials. And there's only 2 outcomes, success and failure. The probability doesn't change from trial to trial. So yes, this is a binomial experiment. It meets all the requirements. So yes, there's only 2 outcomes and a fixed number of independent trials. So yes, there's a fixed number of trials. Does each trial have 2 outcomes, success or failure? Yes. Is the probability of success defined for each trial? Yes. Are the trials independent? Yes. Those are the 4 questions you always ask yourself. That's how you determine if it is a binomial probability problem. Once you've determined that it is, then you can start identifying the values of your variables. The number of trials. How many times is he going to kick the ball? 3 times. What are we counting as success? He makes the kick, right? He scores the penalty kick. That means he scores the point. What's the probability of success? Keeping the wording of your problem. How likely is he to make the point each time he kicks? What's the probability he makes the kick? 60%. And when we use it, we're going to need to use it as a decimal, so we're going to go ahead and change 60% to a decimal, which is 0.6. The last question says, find the probability that the soccer player makes 2 of his penalty kicks. How many successes would that be?
2.
That would be 2 successful kicks. So then the last question is, find the mean variance and standard deviation for the distribution of penalty kicks that he makes. So we don't actually have to put any numbers or use any formulas for the calculator. This is all these three formulas. And since the mean is n times p, that's 3 times 0.6. I'll use the parentheses so we don't get that mixed up with a decimal. And 3 times 0.6, what's 0.6 times 3? 1.8? So we expect him to make 1.8 of the kicks, which means he might make 1, he might make 2. Standard deviation is going to be the square root of n times p times q, which is going to be 3 times 0.6 times 0.4. Now, does everybody know where I got 0.4? If there's a 60% probability of success, that tells us that q is going to be 1 minus 0.6, which is going to be 0.4, or 40%. Okay?
Is that supposed to be in the box?
Not, it will be, yes. I'm just going to calculate it first and then take the square root. Okay? So 3 times 0.6 times 0.4 is 0.72. And remember, that's the variance. So when I take the square root of that number, what I have is the standard deviation. And you would round that off however it says to round it off. Okay? Now, up to this point, all you need to be able to do is find your values for n and p and x, and then be able to plug those into those formulas that I gave you. The arithmetic on those is not easy. Remember, I told you at the beginning, if you can add, subtract, multiply, divide, and take the square root, that's all you need to know how to do. So these formulas are not hard. Okay? Okay, example 4 says we have a probability experiment in which 3 cards are drawn from a deck without replacement. That's important. Without replacement. And the number of aces is recorded. Is this a binomial experiment? Okay, question number 1. Is there a fixed number of trials? Yes. There's going to be 3 cards drawn. Does each trial have 2 outcomes, success or failure? Yes. Success would be an ace and failure would be, no, it's not an ace. So it needs that one. Is the probability of success defined for each trial? Yes. Because there are 4 aces and 52 cards. So the probability of ace number 1 is 4 out of 52. But what is the probability for ace number 2?
3 out of 51.
3 out of 51. And the probability for ace number 3 is 2 out of 50. And that's because of that word that I underlined, those two words, without replacement. Without replacement is not independent trials. Okay? Because that means your probabilities change since you weren't putting the card back in. Okay? Even if you didn't get an ace on the first card, this still changes because whatever you had out on the first card, that is still going to reduce the number in your deck by 1. There might still be 4 aces in there, but there was only 51 cards left in that deck. So are the trials independent? No. And that's because the cards are not replaced as they're drawn. You didn't put them back. If it's with replacement, it's independent. Okay? That was why it was so important when we talked about with and without replacement doing probabilities. It was important that you understood what replacing it did. Now we're going to talk about finding binomial probabilities. And I'm going to go through the first part of this, then give you a little break, and then we'll come back and work some problems. The process of finding the probability involves the considering of all the possible ways there are to select X successes out of N trials. And fortunately, the calculator makes this easy to figure out. We're going to use 2 functions on the calculator. The 2 functions we're going to use are binomial PDF and binomial CDF. Both of those are going to require you to put in 3 pieces of information, and it has to always be in this order. The number of trials, the probability of success, and the number of successes. You always have to be able to identify that. The key thing you need to figure out is what's the difference between binomial PDF and binomial CDF. Binomial PDF is only going to be when you are trying to find the probability that X equals a particular number. Okay? Probability of one particular outcome. Binomial CDF is different because you're going to be finding the probability that X is less than or equal to a given number. Okay? That's what binomial CDF does. If you don't want the probability that X is less than or equal to the number, and you actually, in fact, want the probability that it's greater than or equal to the number, then you use 1 minus binomial CDF. And you're going to have to get those 3 things straight in your head. And the only way to do that is to practice. And note that every one of these involves an equal sign. That's why I brought up that when the probability was less than 4, that was the same as the probability is equal to or less than 3. So you can't use it less thans or greater thans alone. It always has to involve equals to. Okay? So what we're going to do is we're going to try to make statements so that they're going to be ready to plug into the calculator. So keep those notes handy while we work through this one example, and then I'll give you a break. We'll come back and do some others. According to research, about 70% of all United States households have cable television. Part A says, in a random sample of 15 households, what is the probability that exactly 10 have cable? That's going to be important. Exactly 10. First thing we need to do is identify some information. How many trials are there?
15.
15, because there's a sample of 15 households. What's the probability of success, or what is success?
Getting 7. Oh, exactly.
No. Success. You're going to look at each household. What are we looking to see about that household? If they have cable or they don't. Okay? So success means they have cable. Okay? This tells us there's going to be, that we're interested in 10 successes, so you're right about that. What is the probability that they have cable?
70%.
And we're going to change that to 0.7 because we have to use it as a decimal. Okay? And then the last thing is X is what? Exactly 10. So X equals 10. So your probability statement has to be probability that X equals 10. Okay? And the fact that it's X equals 10 tells you that's binomial PDF. Now we're going to use the calculator to actually find the answer. We'll need the calculator. And this is where we're going to find the formula. You press your second and the key next to clear that says bars. It's kind of like diagonally from stat. These two keys are going to be your favorite keys all semester. Stat and the bars key. And on the bars key it says DISTR in yellow above, and that's why I have to press the yellow key. So this is the distributions menu. This is the probability distributions menu. Binom is the short notation for binomial. So we're going to scroll down until we get to the option that says binom PDF. Okay? So we're going to go down and choose that one and press enter. And it wants three things from us. It wants the value of n, which was 15. It wants the value of p, which was 0.7. And it wants the value of x, which is 10. comes back and it gives us the exact binomial probability. We don't have to have all those decimal places. Usually we'll round to 3 or 4 decimal places. So 0.261. And if you write that properly as a probability, then it's going to be the probability x equals 10 is 0.2061. Well, if my math lab says round to 3 decimal places, round like it says to. Okay?
So are those always the same? Like the 0.2061 on the top and the bottom?
Always the same?
Answer?
No. It'll change depending on what these are. It's going to change depending on what the values of success, the number of trials, the probability of success, and the value of x is. That's what we're going to have to practice. Okay? Those are variables. I can show you the formula for binomial probability, but the formula is ugly, and we just assume not to do it. So let's do one more, and then take a break. Part B. Looks like kind of the same setup. In a sample of 15 households, what is the probability that fewer than 13 have caving? What's the number of trials? Okay. Success is if they have cable. Probability of success, it's the same as the probability at the top of the page, it's still 0.7. But now we need to identify the values of x. Fewer than 13. Is 13 included?
No.
No. Do we go up or down?
Yeah.
So our top number would be
12.
so x would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? And I want you to identify it that way. You don't necessarily have to write out all the numbers. You can put little dots in the middle of them, but identify the top number. And remember that your bottom number is always 0, because 0 is always a possibility. It's always possible that you'll not have any successes. Okay? This makes it easier then for you to write your probability statement. Because your probability statement is that x is less than or equal to, because remember it needs to be less than or equal to 12. Even though that said 13, if you'll identify these numbers, you'll get this right. Okay? Now, based on that, look back at your notes that I gave you. Is this binomial PDF, binomial CDF, or 1 minus binomial CDF? It is binomial CDF. And then we're going to use our calculator to find the answer. So we're going to go second, bars, go down and find binomial CDF. It's right after PDF. And we're going to enter in P and x, which is the top number. So what your calculator did was it calculated the probability that x was equal to 0 and the probability that x was equal to 1 and 2 and 3 all the way up through 12, and it added all those together and just gave you the final answer. Okay? And if we round that to 4 decimal places, it would be 0.8732. You had a question?
Oh, never mind, I messed up.
Oh, okay. Did you figure it out then?
Yeah.
Okay.
I thought it was a different binomial, but like I had my sign backwards.
Oh, okay. Now I'll tell you a little trick on this that may help you. Get the calculator out of the way. When you're trying to remember which is which, the first one's easy. It's when it's one number, it's equals. Binomial CDF starts high and goes down. Okay? That means 1 minus binomial CDF actually starts with a bottom number and goes up. Okay? You still have to put the numbers in the same order. It's the subtracting this from 1 that causes it to be the other side. Because what happens here is this goes on up to n, and this on this one goes up to n, but it went down to 0. Okay? So this is when you're trying to find the upper end, and it actually turns out to be, you're trying to find the equal to or greater than, but the way you find it is you find the equal to or less than and subtract from 1. You're taking kind of like the, it's called the complement of it. We talked about the complement, okay? So that little visual might help you remember which one's which. So let's go ahead and take a break and then come back and finish this problem and do the remaining pages, and then see if we have any questions before we finish for the day. So we're still talking about the same problem that we were talking about before. We have a sample of 15 households, and the success is that they have cable. That probability is 0.7. But now we're trying to identify what X is. And it says, what is the probability that at least 8? So is 8 included in the numbers?
Yes.
Yes. So we want 8. Do the numbers go up or down from 8? So 8, 9, 10, all the way up to 15. Okay? So the numbers are going up, and our bottom number is 8. So our probability statement is that, what is the probability that X is equal to or greater than 8. Does that make sense to everybody? And based on the fact that this one always says equals, it only has one number. This one says equal or less than, so in other words, it starts at a number and goes down. This is the one that starts at a number and goes up. And that means that's the option that we're going to need to use. Okay? So on the calculator, what we're going to do is we're going to enter 1 and then subtract. Then we're going to go binomial CDF. And we're going to enter 15 for N and 0.7 for P. And since 8 is included, I'm going to put the 8. Okay? I think I just messed up, so let me think about this a second, because I think I said that wrong. No, 8 is included in what we want. So this part would have to be only up to 7. I'm sorry. That's because 8 is included going up. That means it's not included going down. And this is the part that's actually going down. So this probability x is equal to or greater than 8, which is 1 minus the probability that x is less than 8, which would make the top number 7. Okay? It has to be a complement. We can't include 8 on both ends, so since we're going down, we have to only include 7. Wrong one. So it's 1, subtract, go get your binomial CDF, and then it's 15.7, and then we're only going to go up to 7. Since that's 9499, and the next number rounds up, then we would actually call that, if my math lab tells you to round, that's going to have to be 950 or 9500. Let me see if I can give you another way to get, because this is the part that's the hardest to figure out. You always start with 0. You always end with n, whatever the number of trials is. Somewhere in between there, there's going to be an x. Okay? In this situation, our x was 8. and n went up to 15. What we were looking for was that. Okay? That's what we wanted. But since binomial CDF is the only option we've got besides equals to, the complement of probability x is equal to or greater than 8, which is the numbers 0, 1, 2, 3, 4, 5, 6, 7, means that I have to end this part with 7. So those two are complements of each other. The probability for the whole thing is 1. So there's this part of the probability and this part, and these two have to add up to 1. If you're going to include 8 here, you have to include 7 on the complement, not 8. 8 can't be counted in both places, okay? So that's why we did this.
So what would be the correct way to write the actual answer out? With the 7 though?
With the
like
7.
1 minus B.
It would be 1 minus binomial CDF, 15.7, and then 7. Okay? When it's an at least problem, what you're going to have to do is you're going to go to the number less than that for your CDF command, and then subtract from 1.
Okay, so if it asks like number 2 would there, would you rather it be like the 8 or the 7, or can you use both of those?
Actually, you have to use this one.
Yeah, that's what I was asking.
Yeah, you have to use that one. Even though these say the same thing, remember the calculator only does the equal to. So you've got to have the correct equal to statement. And since we include 8 on the upper end of it, then we can't include it on the lower end. So your top number would be 7. Okay? Now that's going to be the hardest one. And what you'll have to remember is that what tells you, one of the trigger words that will tell you is at least. Anything that says go up, you're going to have to do 1 minus binomial CDF. And if it's at least 8, you're going to have to take the number that's less than that and go down. Okay? Because this is your binomial CDF part. And that 1 minus is where this is. So let's practice a little bit more, make sure you got it. According to Crime in the United States, 1998, about 60% of murders are committed with a firearm. Suppose 14 murders are randomly selected. Find the probability that exactly 13 murders are committed with a firearm. What's N? Randomly selected usually tells you what N is. And remember I said, success isn't always good and failure isn't always bad. Success. What is success? What are we counting?
Someone got murdered with a firearm.
Okay, so they were murdered with a handgun. Okay, or with a firearm.
Yeah.
A firearm. Which might not have been a handgun, it might have been a rifle. But it was some type of bullet that caused the problem. P is the probability that the murder was committed with firearm. What is T?
Point.
Okay? And the one that we're looking at, it says exactly 13. X equals 13. And because it says equal to, then we choose binom PDF. P is one probability. So that's actually exactly 13 is kind of a low percentage. And it says round to 3 decimal places, so 0.007. Okay? Next one has the same setup. N is still 14. Still talking about a firearm being success. And the probability is 0.6 that the firearm was used. But now the question is, what is the probability that 8 or more? That means X is going to be 8, 9, 10, up to 14. Okay? So even though that says actually equal to or greater than 8, we can't put it in the calculator that way. Okay? So the complement of equal to or greater than 8 is that X is equal to or less than 7. Which means then we're going to have to use this command to find it. Because the CDF goes down, not up. Okay? Oops, sorry. And then it says round to 3 decimal places. So that will be 692. Okay? This is the statement of the original question, but this is the statement word so that you can use your calculator. Same setup. Same values of N and P. So N is 14. Success is still firearms. Probability is still 0.6. It says 4 or fewer. Fewer says you're going down. Is 4 included or not?
Yes.
Yes. The fact that it's going down tells us that that's our CDF statement. So when we round it to 3 decimal places, it is 0.018. Okay? Yes?
So the CDF, you include the 4 in the,
You include the 4 because it's all, when you use your PDF or CDF, either one, it's always going to be an equals to. Now, if we had decided up here that 4 wasn't included, if it had been worded that it was fewer than 4, then we would have only included 3. Okay? This one actually is a little trickier than the others. And I would probably tell you a couple of different ways to do it. But let's talk first about the numbers that we're including. It says the probability between 10 and 12. So N is still 14 and P is still 0.6. What are the numbers from 10 to 12?
10, 11, and 12.
10, 11, and 12. If you only have 3 numbers, honestly, it is easier not to use CDF at all. If you only have a few numbers that you have to add up. Because you can do this one much more easily by finding that the probability that X is equal to 10 plus the probability that X is equal to 11 plus the probability that X is equal to 12, and just add those all together. Which means that you'll just use this. Because we're not going down and we're not going up. We're going in between. Okay? And it's really hard to use CDF to figure out how to do the ones that are between. So the easiest way would be to use binom PDF 14, 0.6, 10 plus binom PDF 14, 0.6, 11 plus binom PDF 14, 0.6, 12. And even though that looks like a lot, it actually goes very quickly on your calculator. there's all three of them and they're added together. And the answer is 0.271. Now, as far as writing it, remember how we write between statements. X is between 10 and 12. Okay?
What about 11? Is 11 go in there?
It is in there because this is all the numbers between 10 and 12. You start at 10 and you go to 12, and the only other number in there is 11. Okay? Any questions? Okay, we're still working with the same probabilities, the same successes and failures. So we have 15.
Isn't it 14?
Yes, it's 14. Sorry. Now read the statement carefully. It says, find the probability that exactly 10 but then read what it says about how they're done.
They're not.
Not committed with a firearm. What is success now?
0.4.
That's right. Probability of success is 0.4 because this is not firearm related. Okay? So you have to read your question and then adjust your success statements. So this one is going to be binomial PDF, but what's going to change still same number of trials, but the probability of success now is different. And that probability is 0.014. Okay? Now the rest of them, I'm not going to do the probabilities. I want to walk you through just how to put it in your calculator. We're not actually going to do the numbers. I'm sure you can do those, but I want to make sure that you've got these. According to the U.S. Department of Commerce and United States Census Bureau in 2012, the percentage of people living in Tennessee that are under 18 was 23.1%. And we take a sample of 52 people. Find the probability that 16 are under 18 years of age. That percentage is your probability. So that's 0.231. So this is because it's exactly 16. The then that's how you would write your statement. I'm gonna let you get the numbers. Because if you got this, you should be able to get the numbers and do those correctly. This one says less than 8. What numbers are less than 8? Up to
Less than equal to 7.
less than or equal to 7. So that's going to be binomial CDF. And it's going to end with 7. $14 or fewer. Is 14 included?
Yes.
Up or down?
Down.
Down. More than 25. Up or down?
Up.
Okay. And is 25 included? So that's equal to or greater than 26, but because it goes up, then our statement is the probability that X is less than or equal to 25, and we're going to subtract it from 1. Okay? We're doing the complement. Okay? $18 or more. Up or down?
Up.
Include the 18?
Yeah.
So that's going to be 1 minus probability that X is equal to or less than 17. That's the complement of equal to or greater than 18. At most 6. Up or down?
Down.
Is 6 included or not?
Yes.
Yes. Less than 32, that's going down. Is the 32 included? No. So that's equal to or less than 31. Are not under 18 years of age. What changed?
The probability.
Percent. Now, you can go ahead and calculate that before you do the problem, or you can do it this way. And if you put it in exactly like I just wrote that, it will give you the right answer because it will do this subtraction before it calculates your probabilities. And then this one says at least 20. At least means we're going up. And 20 is included. So that means we're going to do 1 minus binom CDF and then our top number is going to be 19 because the complement is the probability that x is equal to or less than 19. Okay? And I believe that's it. I will have the answers posted to your practice test later on this afternoon, so you can go ahead and start checking and start working on it. Don't forget to review exam 1. Yes, we turn it in, but it's, I mean, even though I'm giving you the answers, you turn it in and it's like a pre-proof way.
Thank you.
It's